Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module of mechanics of bodies we are going to start with the key topics of the Newton's laws as well as the laws of gravitation. So as I just mentioned, so we will start with the Newton's law to begin with, okay, and later on we are going to look at a special case of the Newton's laws, that is the laws of gravitation. Okay, so quickly I just want to summarize what were the three laws of Newton's. So let me just short notate it with NL. So in 1687 there were three laws that were formulated by Newton. The first law said that in the absence of any net forces, the body is going to be in rest or in a state of constant velocity, right? Or in other words, when all external influences external influences of the body or on, well, right now we are just concentrating on a particle, and then we'll generalize the concept of a body through the concept of a particle. So when all external influences on a particle are removed, the particle moves with constant velocity. Okay, so this velocity may be zero, which means the particle may also be in a position of rest. Okay, and then the second law is the one which is more popularly used, which says that when there is a net force acting on the particle of mass m, then it generates an acceleration, let's say of value a, right? So when a force F acts on a particle of mass m, it moves with an instantaneous acceleration a, which is given by F over m. Well, that's the other way now. It is given by the force F over m. Okay, so and then the third law says that every action has an equal and opposite reaction. So that's the short statement of the third law. To elongate a bit, it says that when two particles exert forces on each other, these forces are equal in magnitude and opposite in direction. Equal in magnitude, and the second is opposite in direction, and the third point is that the direction of the force is along the line parallel to the line joining the two particles, right? So acts along the line parallel to the straight line joining the particles. Okay, so joining the particles. Okay, so so just some key thoughts about these laws. So for example, especially a key thought process for the third law is that suppose a typical question that can come to the mind of the student is that suppose two forces which are acting are equal and opposite, as the third law says, then how is net motion possible, right? So if you have two forces which are acting on the particles which are equal and opposite, right? So that is, which means that the net force is zero. So if the net force is zero, then from the second law or even the first law, there is no motion at all, right? So how is motion possible? How is acceleration possible? So the answer to this question lies in the fact that the two forces that are acting on the body, they are acting on two different bodies, right? So if we have, let's say we rename the two bodies 1 and 2, and then we have the first force F12, which is the force acting on the body 2 by the body 1, and then the other force is F21, which is the force acting on body 1 by body 2. Then it turns out that these forces, although they are equal and opposite, they are going to act on two different or two separate bodies, right? So the moment the forces are acting on the two separate bodies, then it creates motion on the respective bodies, which will be clearly dependent on the respective masses of the body, right? So that's how the motion is possible. So suppose we push a chair, the chair is also pushing us back, but we expect that our weight is more than the weight of the chair. So our motion due to the pushing of the chair is negligibly small compared to the motion of the chair through our push, because of the weight of the chair, which is smaller than our weight. So it all depends. So let me just briefly quantify as to what I just said regarding the third law. So what I just said is, so we call this as the law of mutual attraction. Mutual attraction, or which relates the masses and the force on the bodies, right? So what it says is that suppose we have two particles which interact with with interaction forces P1. Well, we are going to name the two particles as particle P1 and P2. Okay, so the two particles, they interact with each other, and P2 induces an instantaneous acceleration A12 on P1, right? And P1 induces an instantaneous acceleration A21 on P2, right? So as I just said just now, we saw that due to third law, the forces acting on both the particles are equal in magnitude and opposite in direction with respect to each other, right? So we expect that so P2 induces an acceleration on P1. So we have, due to A12, the acceleration A12, we have the net force F12 given by M1 times A12, right? Because we have, why M1? Because we have the particle of mass M which is acting on P1, right? And similarly we have F21, which is M2 times A21, which is the particle, which is the force acting on the particle P2. Now due to third law we have F1 2 is equal to F21, or what we have from here is that A12 ratio A21 is M2 over M1, right? So what we see is that due to the interaction, the relative ratio of the acceleration, I should just put an absolute value because we are talking about the magnitude of the acceleration. So the relative ratio of acceleration, the magnitude, depends on the ratio of the masses in an inverse fashion. Okay, and that is what the law of mutual attraction means. So yeah, and then we can just say that this ratio of accelerations are completely dependent on only the masses. It doesn't depend on other external factors like velocity, position, and so on and so forth, right, of the individual particles. So the ratio only depends on the masses. Okay. So also there is one more point regarding the third law. As I just said that since the forces, the interacting forces are acting on two separate bodies, and that creates an unequal motion depending on the masses of the body. This question also arises as to what frame of reference we are talking about. When we are talking about motion of bodies, we also have to fix the frame of reference, right? So suppose we fix the frame of reference with the body itself, then we won't see the bodies moving at all with respect to the frame of reference. Or in other words, if the frame of reference is fixed, let's say absolutely fixed, then we are going to see the body which is moving with respect to that frame of reference, right? So what I'm just trying to say is that the frame of reference is an important entity that we have to be worried about when we are talking about the kinematics of the body, right? So let me just introduce the concept of frame of reference. So let us start with the so-called inertial frame. Inertial frame. So it says a reference frame in which the first law is true is said to be an inertial frame, right? So a frame in which there are in the absence of any net forces, the particle does not experience an acceleration, right, is the so-called inertial frame. Now it turns out that suppose, let me just show you what I am trying to highlight. So suppose we have an inertial frame. Let us say this is my inertial frame, right? And let's say after some distance, and this inertial frame has an origin O, and some distance away from the inertial frame we have another inertial frame which is, let's say, fixed with respect to the first inertial frame IF1. So now we have another inertial frame which is at a distance d from the first one, which means that similarly we can create more inertial frames and so on, and the motion with respect to the first inertial frame will be identically equal to the motion with respect to any of the other inertial frames. Or in other words, what I am trying to say is that inertial frames are not unique, right? Especially if when the frames are not accelerating with respect to each other. So so this is the law of inertia, which says that basically it says about the non-uniqueness of the inertial frames, right? If we have one inertial frame, then we have infinitely many inertial frames mutually unaccelerated with respect to the first one. Okay. So now this question comes is, what inertial frame are we going to choose in order to describe the motion? The answer to this lies in the fact that there are several options with us. It all depends what motion we are trying to highlight. For example, if you are trying to highlight the motion of a body, a small body, well, we also have to quantify the word small, But let's say a body like a ball, or a small object like a chair or a table, then we can conveniently keep the inertial frame fixed to the center of the earth, right? And although we know that the earth is also rotating, the earth is also moving, but for small objects we can fix the frame of reference as the center of the earth, and we call this frame of reference as the so-called geocentric frame. Okay. So just now what we just mentioned was the so-called geocentric frame. So by geocentric frame I mean that the origin of the frame, the origin of the inertial frame is fixed at the center of mass, the center of mass of the earth, the center of mass of earth with no rotation with respect to distant stars. Okay. So the geocentric frame says that the origin of the inertial frame is with respect to earth, such that the earth is not rotating with respect to some distant stars. I mean, we always have to talk in relative terms, right? So that is the whole issue about kinematics. And then we also, suppose we are on the other hand we are trying to describe the motion of a satellite, and we are going to come to that issue very shortly when we talk about the law of gravitation. So when we talk about the motion of satellite, we cannot just take earth to be our inertial frame, because as we see that earth is also rotating, then we have to take a frame which is more appropriate for such motions, the so-called heliocentric frame, where the sun or the center of the solar system is the origin of the reference frame, right? So the second option that I just mentioned was the so-called heliocentric frame. Okay. So the origin is at the center of mass of the solar system with no rotation. Okay. With respect to distant stars. Okay. So those are the two standard frame of references. There are many others, but these are the two typically used. Now then the issue, the other issue that we haven't touched upon is that we have described the three laws of motion by Newton, but we formally we haven't come about describing the concept of force. So let me quickly describe formally what is force, right? So force, it is such a fundamental quantity that we have to describe it again through Newton's law itself. So force, the quantity force is the reason for the presence of an acceleration on the body, right? So as simple as that. So the presence of force is the reason for the acceleration of the particle. So the definition of force could also be described through our law of mutual attraction. That is, if two particles, let us go back one page up. In laws of mutual attraction, we had described forces due to the interaction of the particles, right? So if we have forces F12, that is the force acting on particle 2 by particle 1, particle 2 by particle 1, yes, is F12, and similarly the force F21 is the force acting on particle 1 by particle 2, the other way around, sorry, particle 2 by particle 1, and then these are the so-called forces acting on these respective particles of masses m1 and m2, right? So These are the two ways we can describe this so very fundamental quantity force, either through Newton's second law or through the law of mutual attraction. So then this question arises, how about in a real time scenario, right? So before we move ahead, let me just wrap up this first module by saying that in the next module we are going to continue our discussion and we are going to dive into the laws of gravitation. So thank you very much for listening.